in short, what I was saying is that we have more and more detailed observations of the ISM, mapping numerous lines. And of course, to answer actual astrophysical questions, we need the physical conditions, density, temperature. So to do this, we need to use, unless we rely on qualitative proxy, if we want a quantitative estimate of the physical condition, we need to rely on ISM models, which can be of different types and different levels of complexity, excitation and radiative transfer codes that assume that keep chemical abundances as 3 parameters, astrochemical codes, and then codes where the stratification along the line of sight is described, the physics that controls it is described, for instance, PDR codes like the Meudon PDR code, H2 region codes like cloudy, where the stratification along the line of sight is controlled by the penetration of UV photons, or shock codes, where the stratification is controlled by the shock front and then the cooling of the gas in the post-shock gas. Now, you have a model that goes in this direction. From physical condition, it predicts observable quantities. So if you want to go in the opposite direction, you need some inference methods, which can be either from the simplest method like chi-square minimization, or more complex methods like Bayesian inference that allow to get the full information about the uncertainties. The issue is that all of those methods will require several estimations of the ISM model, especially Bayesian inference method using MCMC sampling. And this can become an issue because the computation time of those models is not negligible. So in this presentation, I will talk about 2 things. First, I will present the Meudon PDR code as an example of those kind of complex ISM codes, focusing on the physics and the chemistry that's included in the model. And then I will describe the efforts we've made to develop some form of emulator of the model to replace it during sampling for Bayesian inference, for instance. So let's start. Let's start with the Meudon PDR code. So what is the Meudon PDR code? It's a state-of-the-art model of UV-irradiated neutral atomic and molecular gas that's been developed for decades now and which is public since 2006. So the code is public. We also publish grids of models that people can use and tools to compare those grids of models to observation. So now, UV-irradiated neutral medium, the most typical environments are what we call dense photodissociation regions, or PDR, that occur in star-forming regions and that constitute the interface of molecular clouds where they are subject to stellar radiative feedback. So at the border of H2 regions usually. So those regions have warm and dense molecular gas, so they have very rich emission spectra, both in the infrared and in the millimeter range. And they are very interesting to study for 2 reasons. First, of course, to probe directly the local effect of radiative feedback on the state of the molecular gas, but also because they constitute an ideal laboratory to study the processes that govern this interaction. And this physics is actually, the physics of PDR is actually present everywhere in the ISM, from the smallest scale, irradiated protoplanetary disks, for instance, to the largest scales, where in galaxies, some part of the infrared spectrum are dominated by emission from PDRs. So in a PDR, the stratification, physically and chemically, is controlled by the penetration of UV photons that will dissociate, ionize, heat, and pump species in the gas. And so at first order, the physics is intrinsically 1D. So the Meudon PDR code is a 1D model with a spatial dimension that is the depth into the PDR. Then photoprocesses in the regions where the physics and chemistry is dominated by the impact of UV, the photoprocesses induce short time scales so that at first order, the PDR structure can be considered as stationary. So the Meudon PDR code is a stationary model. And so where is the complexity of the model? It's in the fact that we focus on the exhaustivity of the physical and chemical processes because, as I said, the PDR physics is applicable in a very wide range of environments. And so we want to avoid using approximations because approximations have limited ranges of validity. And so we need to describe as accurately as possible the different physical and chemical processes and their couplings. So a PDR model, what does it describe? It describes a 1D slab of gas that's irradiated in UV. And so the parameters that control the models will be parameters that control that describe this slab of gas. So either the density, if we do a constant density model, or the thermal pressure, if we do a constant thermal pressure model. And in dense PDRs, usually the description with a constant pressure is better. And then the thickness of the slab described by its total AV. And then the UV field, we can have different geometry of irradiation, different spectral shapes, but at first order, it's described by the G0 parameter, which gives the ratio of the energy density in the FUV domain compared to the typical ISRF. There are, of course, other parameters that we can vary, but I won't talk too much about it, like the metallicity, the dust properties, or the cosmic ray flux. And then what the code computes, it computes both at each position along the spatial dimension, the physical and chemical states. So we get profiles like temperature profiles and chemical abundance profiles as a function of depth, but also the escaping spectrum, both the emission lines and the continuum. So we get model predictions that are directly comparable to observations. To do this, it solves 4 main parts of physics: radiative transfer, chemistry, thermal balance between heating and cooling processes, and excitation of the different species in their quantum levels. I will give a bit more details about each of those. So the radiative transfer is solved from the UV domain, only the non-ionizing UV, to the radio domain. It's described in a fully wavelength dependent way with a grid of several thousands of wavelength points, because one very important process in PDRs is the dissociation of H2 by UV photon, which occurs through the absorption of UV photons in lines exciting H2 in electronic excited states that can then de-excite towards a dissociated state. And so we need to resolve those absorption lines. We need to have a full wavelength dependent radiative transfer. It includes both extinction and anisotropic scattering by dust. So anisotropic scattering by dust means that we need to have a description of the angular distribution of the radiation field in our medium. We do this with the spherical harmonics decomposition of the angular distribution. And not only extinction and scattering by dust, but also extinction by the gas, both in absorption lines, as I said, for H2, and with, there is no animation. Okay, we were supposed to see here as we move in depth into the PDR, the local spectrum of the energy density in the UV domain, and see as we move in depth inside the PDR, see the absorption line of H2 that gets deeper and broader. So not only in lines, but also in the continuum with the photoionization of some species. And this radiative transfer also includes the emission of the local emission of infrared by dust inside the PDR. Then chemistry with several hundreds of species, several thousands of reactions, including isotopic chemistry and also surface or ice chemistry, for which we have not a single dust grain size, but a dust size distribution with size-dependent grain temperatures that are computed. Then the thermal balance of the gas is computed, including several multiple heating and cooling processes. Of course, the photoelectric heating, but also heating by H2 UV pumping, where H2 is pumped to electronically excited state by UVs, de-excite to vibrationally excited states, and from there, so by fluorescence, and from there it can de-excite collisionally to lower levels, and so transmit part of the energy of the UV photon to the gas to heat the gas, and other processes like photodissociation heating or H2 formation heating. Cooling, of course, is mainly comes mainly from emission lines, so tens of species are accounted for, and there are other processes that can either contribute to heating or cooling, like gas-grain collisions. And then combining all of those, we compute at each position in the cloud the temperature that balances heating and cooling, just to show that, so this is only for the very edge of the atomic region, showing that depending on the condition, density and G0, it's not the same heating and cooling processes that dominate. And the last part, as I said, is the computation of the level populations of the species. And this is done in a non-LTE way, so including collisions with the different collider, radiative transition, including also UV and infrared pumping, but also the fact that species can be formed by chemical reaction in excited states. So this is sometimes called chemical pumping, and also the reverse, that the destruction of species can be more efficient in some states. It can be important, for instance, for H2, where also H2 can self-shield faster, and so be less, in some very specific region, will be less photodissociated than para levels of H2. This, of course, requires large amount of atomic and molecular physics data, spectroscopic data, and we constantly keep those up to date. And this is a list of the species for which we can compute the level population. Now, I want to emphasize the fact that the Meudon PDR code is not just a chemistry code with a radiative transfer and excitation code put on top, and so on. There are actually very complex couplings between all of those components, and I will give a few examples highlighting this. For instance, photoreactions very often are described with a simple AV-dependent law, but actually they can have quite complex cross-sections. I show a few of them here, where we see very strong resonances, and we can take those into account because at each position in the cloud we have the wavelength-dependent radiation field, so we can directly integrate those cross-sections. And this is important because, as I said, in the UV domain, you have very strong H2 absorption lines. So you see, for instance, at one position in the PDR, the UV spectrum with those H2 absorption lines. And depending on whether those resonances in the photoreaction cross-sections fall inside or outside the lines, it can very strongly affect the photoreaction rate, and we see that sometimes it can affect, as a result, the abundances of the chemical species. Another example of those coupling, the photoelectric heating mechanism, which is one of the main heating mechanisms in the ISM. So it comes from ejection of electrons from the grains due to UV photons. Of course, those have wavelength-dependent cross-sections, so they are coupled to the radiative transfer, but they also depend on the charge state of the grain. And to describe this, we need the other processes that affect the charge state of the grain, the recombination with ions and the recombination of electrons. And so this will couple to the chemistry. And to add some more complexity to this, the problem is that for small grains, the typical charge of a grain will be of order 1. So fluctuations, discrete fluctuations, need to be accounted for. And so what we need to solve at each position for each grain size is actually a charge probability distribution. And one last example, state-to-state chemistry. So some reactions have high activation barriers. For instance, the formation of CH+ is a famous example, where the formation from C++ plus H2 has an activation barrier of more than 4,000 Kelvin. So in typical conditions, it's not very efficient. But in PDRs, H2 is pumped by UV, which then by fluorescence will populate vibrationally excited states. And H2 in vibrationally excited state contains enough internal energy to make this reaction exothermal, and so it can activate the reaction. This is the very same processes that dissociate H2. When you excite H2 to an electronic level, a fraction will dissociate, but most of the time it will actually decay by fluorescence to a vibrationally excited state. And this is true for many other reactions, and so chemists have computed state-to-state rates, and we can take this into account, and this couple the excitation of molecules in the code to the chemistry. And this can make significant differences in the abundances of this molecule. And in particular, this was critical for the explanation of rotationally excited CO lines with air shell in PDRs, that actually to explain them, we needed to open those pathways to create those molecules that would then help create CO very close to the edge in very warm gas. And this is also useful for planning ALMA observations of species like SH+. I won't talk more about applications of the Meudon PDR code. You will have several this afternoon with the presentation by Aurélien Piluso and by Pierre Palou. Now that you know what's inside the Meudon PDR code, let's come back to our initial problem. So we want to do Bayesian inference with the Meudon PDR code. So we need to be able to do a large number of evaluation of the model for different values of the parameters. And this number will be especially large when we want to do Bayesian inference on observation maps, especially if we have some coupling between the pixels, like will be presented by Pierre Palou in the next talk. There are also other statistical approaches that can require sampling with the Meudon PDR code, and you will see an example in the presentation by Luca Heinig. The problem, of course, is that the Meudon PDR code takes several hours per run, so it's completely impossible to use directly for sampling. What's been used usually is to have pre-computed grids of PDR models exploring some parameter space. So I give a very simplified example here, where we have a grid of model exploring density and G0, and for each of those, we know the predicted line intensities. And then the idea was to use simply interpolation between those points when you did to estimate the model at some physical conditions. Now, this can have several issues. First, depending on the coarseness of this grid, it can have actually non-negligible approximation errors. And then even with simple interpolation methods, they tend to still be too costly for Bayesian sampling, especially on large observation maps. Now, the idea is that actually we have no reason to limit ourselves to interpolation. Any approximation method can be used to build an emulator of the code that we can then use for sampling. And so this becomes a regression problem for which we can use classical machine learning methods such as artificial neural networks. So the work that I will present now was led by Pierre Palou and Luca Heinig, but because I have other things to present in the next talks, I will be presenting this. So the goal was to build a fast and accurate emulator of the Meudon PDR code that that can compute all of the lines that the code can predict, so more than 5,000 lines. And we explored a wide parameter space with 4 physical parameters, thermal pressure, G0, AV, and the viewing angle of the line of sight relative to the PDR surface. We tried to build our emulator using an artificial neural network, a simple, fully connected feed-forward neural network. I give a simple example here. The idea is that at each layer, you combine the values that you have linearly, and you pass them through a simple nonlinear function. And the idea is that by composing this nonlinear function several times, you will be able to have a very flexible fitting function that can approximate any nonlinear function. We use a training set. So for these studies, we actually use a training set that's built as a regular rectangular grid only because we wanted to be able to compare it to usual interpolation methods, and some of those require a regular grid. And then the test set is just randomly drawn inside the domain of the grid. Okay, so to design this neural network, we combine several strategies. First, one very important aspect is outlier removal. The problem is that in some specific region of the parameter space, some of the lines predicted by the model can be affected by numerical issues. And so this gives outlier values. Now, with the usual loss functions that are used to train neural networks, like the typical squared error that's here in orange, you penalize a lot large errors, meaning that you would rather have a network that's off by a bit on all of the points, rather than having a network that's very good on most of the points and very bad on a few of them. So in general, this is good, but you can have other loss functions that are very flat for large errors, meaning that you are saying, okay, if I fail on a point, I might as well fail by a lot, and I would rather have most of the points well reproduced and a few of them not reproduced at all. And we exploit this by first training a first version of the network with a robust loss function like this, because then the outliers will stand out naturally as point of the training set that have very large reconstruction error. We can then inspect them visually to check if it's true physical discontinuities or actual numerical issues and eliminate the points that are affected by numerical issues. This is a very small fraction of the values in the training set, but it actually makes a very strong impact on the result of the network at the end. Another strategy that we used is polynomial input augmentation, because we have a somewhat unusual situation where we have a very small input dimension and a very large output dimension. We have a physical model that has very strong linearities, but we still want a lightweight neural network. So we can help the network by providing in input some pre-computed simple nonlinear combination, polynomial combination. So to give a simple example, instead of giving two variables x and y, we give x and y, but also x squared, y squared, xy, and so on. We go up to order 3. And this also improves somewhat the accuracy of the final network. Another strategy that we used is that if we compare to interpolation methods will necessarily treat lines individually. But actually, the lines predicted by the code are correlated. They share information, and we can exploit this. So I show here the correlation matrix on the training set of all of our line, and we see that there are regions of high correlation between the line and regions of very low correlation between the lines. So the way we exploit this is we use spectral clustering to define groups of lines with strong correlations. And this way we find 4 groups of highly correlated lines. And we actually, instead of building one large neural network, we build one separate neural network to predict each of those groups, to exploit as much as possible the shared information, but still keep relatively lightweight neural networks. Another way to exploit those correlations is to use it for dimensionality reduction. Using PCA, we can find that among the more than 5,000 lines of the training set, they can be very well reconstructed by a linear combination of only around 1,000 underlying factors, so the principal components. And we exploit this to set the size of the last hidden layer, because usually in regression, the last hidden layer is linear. So what this tells us is that from 1,000 values here, the network should be very well able to reconstruct the 5,000 lines. So this helps us scale the size of the layers in our network. And then finally, we use to avoid some potential issues like the gradient vanishing issue and the difficulty sometimes to reproduce very simple relationship when you have a deep network. We use the dense net architecture, where instead of each layer taking as input only the output of the previous layer, each layer actually receives as input the output of the previous layers, but also the input of every previous layers. And this helps making networks that are quite deep, but with not too many weight coefficients, and so easier to train. And so the final architecture combines all of those strategies with 9 hidden layers and a layer size that increases following a geometric progression from the size of the input to the size of the last hidden layer that is set by PCA, as I said. And of course, we do this for 4 separate INNs for the 4 groups of lights. And here are the results. On those figures, I compare typical interpolation methods to our neural networks in orange. So blue are the interpolation. Orange are our neural networks. There are many points because we see as we progressively introduce each of the strategies that I discussed, that we get better. And so the result is that we get an emulator that is more accurate on average than any interpolation method using the same grid as the initial training set, with errors lower than 5%, which is sufficient typically. For instance, the calibration uncertainties of the observation will be of this order. It is also significantly better in the worst case error, so using the 99th percentile error. This is very important because you can have an emulator that's very accurate on average, but if it's sometimes very wrong, it's a problem. Here we know that in the worst case scenario, so the points that have the 1% point with the largest error, the error is still of the order at most of 30%. And at the same time, it is much faster than interpolation methods, and lighter in memory because, of course, interpolation method need to keep the full data set in memory. And so to conclude, what I presented about the Meudon PDR code is summarized here. You have the links where you can access the public code, the public grids of models. And the important part about the emulator strategy is that it's actually, I described it for the Meudon PDR code, but it's actually applicable to any ISM model. It's not limited to the Meudon PDR code. It's available as a public Python package called NNBMA, which you can find here. And as I said, it beats interpolation in both accuracy, speed, and memory rate. Thank you.
Thank you, Emeric. So is there any questions to Emeric? Yes, Frédéric.
Yeah, thanks. It's a very practical question. So when you make an update of the Meudon PDR code, even a minor one, do you have to retrain the whole network, or can you update also your network?
No, indeed, each time we haven't done it yet, but each time we publish new public grids of models, we need to train an associated neural network, yes.
Other questions? In Zoom? No. Okay, so I have a question, Emeric. If we want to use NNBMA, and if we have difficulties, is there still some support for NNBMA?
So NNBMA was developed by Pierre Palu and Luca Hennig, who now both work in the industry, but I think they are still providing some support when they have time.
Yes, we do.
And otherwise, Aurélien Piluso has been using it for applications of the Meudon PDR code, so he can also help. He has some experience using it.
Patient is already available.
Okay, thank you. Thank you, Emeric.
You said that sometimes you detect outlier in the emulator. Have you ever detect outlier and check in the physical model if it's very a numerical issue, or are you ever detect physical processes that you haven't take into account, or?
So indeed, it's very important to check. And Pierre went through checking all of the outliers, all of the potential outliers, because we can have physical discontinuities across the parameter space, in which case we shouldn't eliminate the point. So Pierre actually looked at each of those points to check if it was a physical discontinuity or some numerical issue.
Okay.
Great talk, thank you. I was wondering, you showed at the beginning that several non-LT mechanisms were taken into account for H2 excitation. Do you also plan on implementing such mechanisms for other molecules?
Which mechanism, sorry?
The non-LT excitation, all the collisionals, all the collisionals you stated for H2. Are you taking into account such rates for other molecules?
So currently it's done non-LT for all the molecules for which we compute the excitation. It's true that for state-to-state chemistry, we have mostly reactions with H2 for now, but some other reactions can be implemented.